Hello everyone, I'm Hongshou Wang. Today I'm going to present a very interesting paper, which was written by the Li and Professor Dan-Qing Chen from Korea and Princeton University. This paper also have been referred in many previous papers, such as UC topic. I think their work also be one of the most influential work in the open domain question answering in recent years. The project is open source, and you can easily find their code and datasets through GitHub. I also give out the GitHub link here, just in case if someone is interested. By the way, they also provide a wonderful live demo. You can also play with it. So before we talk about the paper, there are a few background that I think that may be helpful to better understanding the paper. First, I'm going to introduce one of the most hot topic in NLP community recently called open domain question answering. Briefly speaking, given a question as an input, you want to teach a machine to answer the question based on your closed book knowledge, like trained parameter, or open book knowledge, like Wikipedia. Question answering QA aims to provide a precise answer in response to user questions in natural language. Compared with the search engine, the QA system aims to present the final answer to questions directly instead of return a list of relevant passage or hyperlink, thus offering better user friendliness and efficiency. OpenQA tries to answer a given question without any specific context. The SOTA open question model follows a retriever and reader architecture. Retriever is responsible for retrieving relevant documents with respect to a given question, which can be regarded as an IR retrieval information retrieval system. For different IR systems, depending on their design, they retrieve different types of documents, such as passage or text spans. This paper target phrase spans in a wiki passage, while reader aims at inferring the final answer from the received documents, which is usually a neural MRC, machine reading comprehension model. Mostly, the SOTA MRC utilizes a pre-trained language model like T5 or BART to generate the answer. Since the documents are served as the external knowledge to enhance the OpenQA system, how can we access or retrieve the relevant document comes a problem. Traditionally, methods use this sparse representation to present the document. However, imagine there are 6 billion phrases or 21 million paragraphs need to be retrieved. It's really time-consuming to search through documents. Term mismatch, which is also a long-standing problem that harms retrieval performance. Unlike the traditional methods such as TF, IDF, and BM25 that use sparse representation, deep retrieval method learn to encode question and document into a latent vector space. Encoders to encode each document and question independently into dense vector, and the similarity score between them is computed using inner product of their vectors. The sublinear max inner product search MIPS algorithm is used to improve the retrieval efficiency given a question, especially when the document repository is large scale. You may ask, why not utilize only pre-trained language model like BERT to take question concatenated by the corresponding document as the input to calculate the corresponding similarity score, like Graph2 in the site. This method, although it has a better performance compared with dense-based retriever, but usually require heavy computation and hard applied to large-scale documents. Dense retriever makes a trade-off between sparse and interaction-based retriever, which extracts the document efficiency and preserve high accurate and FE score. Before going back to the paper, let's finally talk about the SOTA model, which this paper tried to compete with. It's Professor Dan-Qing's previous work, Dense Passage Retriever for Open Domain Question Answering, also called DPR. As you can see in the graph, dense retrieve has been shown effective in open domain question answering and many other knowledge-intensive NLP tasks. Once we get this background idea, the rest of things become straightforward. In order to improve her previous work, we may ask some questions. Why dense phrase retriever, not dense passage retriever? What's the improvement of the dense phrase retriever? How to do that? How to implement that? Let's first answer why dense phrase retriever. The answer is pretty easy. It's more efficient than the DPR during retrieving or during retrieval. Just think of encoding size of the document. In dense phrase, their setup is only 20 words, but in DPR, encoding passage contained 100 words. Encoding the phrases save lots of time during training and testing. Although the size of overall representation increased from about 1 gigabyte to about 300, from about 100 gigabyte to about 300 gigabyte. The preprocessing speed is really amazing. I actually ran their demo to see how fast to extract the documents. The speed really surprised me, and in the video, from my experience, there are almost not latency between typing each token and the corresponding documents immediately shows up. They also evaluate the dense phrase model on 3 tasks. First is open domain QA. Without any sparse representation, dense phrase outperforms previous phrase retrieval model by a large margin and achieved a 20% absolute improvement on overall dataset and competitive with DPR. Our model, their model also achieves the best performance of 78.3 EM on SQL-AD dataset and improving the previous phrase retrieval model, dense SPI by 4.7%. Although it is still behind the cross-attention models, the gap has been greatly reduced and serves as a strong starting point for the open domain question answering model. For slot filling tasks, their model achieves the competitive performance on all datasets and achieves state-of-the-art performance on 2 datasets using only 5K training example. In this paper, the basic architecture is straightforward and close to DPR model. They adapt the dense-based architecture using MIP MIPS to compare similarity score, but this time they encode the phrase, not the passage, which saves lots of time to retrieve the document and get competitive results without the DPR model. The main technology contributions of dense phrases can be summarized as follows. Motivated by the literature on the constructive learning, we can treat all the gold phrases from other passage in the same mini batch as negative example. So we call this as in-batch negative example training strategy. In each iteration, we maintain a 5-fold query of mini batches to cache phrase representation. The cached phrase representation are then used as a negative example for the next iteration. We call this the pre-batch negative training strategy. So third, they also find that generating question for every entity in training passage improves the quality of phrases representation where they use a question generation model based on T5. So both training strategy are verified by the ablation study in the paper. From fine-tuning side, due to a large number of phrases representation, they fix them once they are applied and further optimize the question encoder. This is shown to be better effective for in-domain dataset as well as the transfer learning. In this regard, they can view their model as a dense knowledge base that can be accessed by many different types of queries, and it is able to return phrase-level knowledge efficiently. So in conclusion, dense phrase is an extractive phrase search tool based on natural language input that achieves dense retrieval of billion-scale phrases with extremely runtime efficiency. However, the model is still memory intensive, which requires about 300 gigabyte storage on the drive, and not outperform SOTA model like DPR. But the incredible accent speed has already given enough credit to this paper. I really appreciate them to make this paper public, and we can access their code. So the last slide is just about the reference. Thank you for watching.